Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about what is a Hall voltage and basically applying electric field and magnetic field on moving charges. Moving charge particles. So let's take a look at this question. It's a very classic question, and it's got some interesting applications. So it's a typical what an IB question would love to do. IB questions love to take something in real, like a real life situation, and try to adapt it, simplify it enough so that they can use that on you in a way. So sounds a little brutal, but here we go. So here's a Hall voltage question. It's got some points on the side, which I think some of them are a little bit incorrect, but let's, a lot of questions, so let's quickly get started. So a bit background information. What this Hall voltage is kind of like the Hall, it's based off of the Hall effect. What's going on is that we run a current through this conductor. It's a long strip of wire, or actually it should be a plate. It's probably easier if it's a plate because then you can see the effect clearly. So after running this current, we apply a relatively strong magnetic field across the plate. And of course, due to the magnetic force and using your right-hand rule, you'll be able to figure out the direction of which the charges are going to bend inside this conductor. So depending on what charge is actually moving, the magnetic field is going to affect which side collects all of these charges. So let's say my calculator here is the conducting plate, or the conductor. So as charge is moving through, if a magnetic field is applied here, then the charges, depending on if it's a positive charge, it might collect on the top side of the plate, or if it's negative, might collect on the bottom side of the plate, or vice versa. Actually, if the current is in the opposite direction, then you might see a different effect. So essentially, based off the Hall effect, you get a collection of charges on one side of the conductor, which then you can measure using just to test the potential difference. And from testing the potential difference, you can then say, the charge carriers are actually negative, or are they actually positive? So we get to answer that basic question. The interesting thing about the different conductors, some conductors have positive charge carriers, which the Hall voltage, Hall effect can also confirm as well. So the Hall voltage is specifically the potential difference across these two conductors based off the charge that's collected on either side. And yes, it does depend on the current running through the conductor as well, which we will see in a second. So let's begin with this question. Lots to go. A current I is established in the conductor. The diagram shows one of the electrons making up the current moving with drift speed v. So this guy here is an electron. The conductor is exposed to a magnetic field at right angles to the direction of motion of the electron. Here they show it in this diagram. On a copy of the diagram, draw an arrow to indicate the direction of the conventional current in the conductor. Okay, so this question basically is asking you, do you know that the conventional current is actually opposite to the direction of electron flow? And hopefully you would know that, and so you would somewhere indicate that the conventional current is backwards. So I'm just gonna note that there using red, and that knowing the correct direction gives you 1 mark. And 2, the magnetic force on the electron. So here you will need to use the right-hand rule, and I'm not going to try to demonstrate it in front of the camera because of the mirror effect. It's going to look very bad. But essentially, imagine you have 3 fingers, and guess what? It's an electron. So I'm going to use my left hand. It's going to look like I'm using my right hand in the camera, I think. So I am actually using my left hand. So left hand for a negatively charged particle. So you want the thumb to be the direction of the electron, the charge. Okay, you want the index finger to be the direction of the magnetic field, and the middle finger is going to be the direction of the force. So if I am doing this correctly, okay, you might have to do some weird elbow movements. Yeah, so it looks like the magnetic field is gonna push these electrons to the top. So the direction of the force, magnetic force, I'm gonna use, actually I'm gonna use green, is going to be to the top of this conductor. So that's gonna be Fm for me. Then I'm gonna write that down here just to show what it is. Okay, let me just double check with my other finger because my left arm is weird. Okay, so there you go. So don't be afraid to kind of like jiggle out of your body motion, your movements, just to get the right positioning. And yes, on the exam, when I see students writing the test, they were doing all sorts of weird stuff, and that's okay because you need to do that in order to find the correct direction here. So B, we're done A now. On to B. Show that the current in the conductor is given by I equals to QNAV, which I'll do down here. Q is the charge of the electron. The A is the cross-sectional area of the conductor. V is the drift speed of the electrons. And N is the number of free electrons per unit volume. Okay? So, let's take a look at, let's see. Am I going to have enough space? Okay. I'm going to use this segment here. Okay? I'm going to use this drawing because it will hopefully make our lives easier. So let's say, okay, that's the D here. So let me take a chunk of this metal, this conductor. Let's take this part here, okay? So let's take this chunk of metal. And let's say that in this chunk of metal, there is some number of electrons, okay? So that's in my little purple dots over here. It's some amount of density. So this density here, so this density is N. Okay, which is the number of electrons per unit volume. Unit volume, I'm just going to use m to the power of 3 for unit volume, for 1 unit volume there. So it tells us the drift velocity here. So it tells us the drift velocity, which gives us, okay, basically the amount of distance that these electrons travel per 1 second, okay, per 1 second. And the other thing they tell us is this cross-sectional area here. This cross-sectional area A, which is essentially just meters squared, okay? So what else they tell us? They also tell us the charge of electron, which is Q, so that's important. So ultimately, we want the current to be the number of charges, or the charge, the total charge, that passes a specific cross-sectional area of your wire per unit of time. Okay, so that's what we want. To find the the total charge, we of course need to know the number of charges that actually pass through that conductor at this region per second. We also need to know how much charge is carried by each charge carrier, which is told to us by Q, which is given in the question. It's the amount of charge carried by each electron. So first of all, we need to figure out the number of charges first, because at the end, if we know the number of charges, we just multiply by Q to get the total Q. So in 1 second, we're going to get, imagine this segment here is exactly how much electrons, or how many, basically the longitudinal distance, that the amount of electrons that I'm grabbing. So in 1 second, let's say this electron here moves exactly this distance, okay? So if that's the case, then all of these electrons in between here, all of these guys would have moved past this cross-sectional area here at the end, okay? So after 1 second, all of these guys, let's say that this distance here is actually equal to V, because if you think about it, in 1 second, these electrons would have traveled that far, so this amount of electrons, or in that space, will pass the cross-sectional area. Okay, so that's going to give us kind of the that's going to give us the distance in one dimension, and then multiply that by the cross-sectional area of the wire is going to give us the volume of electrons involved. Okay, so let's write that down here. Okay, so here I've typed up that in 1 second, the electrons inside the volume of, so basically defining the volume, which is going to be in 1 second, the distance of electrons multiplied by the cross-sectional area. So if we kind of, basically we took this A here, and we multiplied it by V. Oopsies. Let's do that. So this A multiplied by V is going to give us this entire volume. Okay, so by taking that volume, and what we want to do next is that since that volume is going to give that's the volume of interest, we take that volume and multiply that by the density of the electrons in there. It's going to give us a total number of electrons. Okay, so here's how I would write it. Okay, so that, here we go. Multiply this volume by the density of the electrons per unit volume will give us the total electrons passing through that section of the wire per second. Okay, so this is already per second because of the velocity term. And then finally, we just need to multiply these number of charges by the total charge of one electron to give us the total charge. Okay, so that's what I wrote here. Multiply this charge per electron. Multiply this by the charge per electron to give us the total charge passing through one section of the wire per second. And that's the definition of the current, which is the total charge passing through a section per unit time. Okay, so that is equal to I, which is equal to total Q per time. Okay, all right, so that's B. And yes, you might be thinking, yeah, you kind of have to write it down. That's true. Okay, all right, so that's going to hopefully be 3 points. Hopefully, okay? That's 3 steps in our thinking, okay? Notice how I did that there. As I was solving it, it's kind of difficult to kind of, I look at where I need to be, I look at what I have, and then I kind of work my way from the beginning to my end, knowing the end point. So I kind of have to establish 2 points in my thinking, A and B, and my thinking, and the steps. The 3 marks are going to be 3 steps that get me to point B from point A. Okay, so explain by a potential difference why a potential difference will be established between the top and bottom faces of the conductor. Okay, so essentially what's going to happen is as these electrons move, and because it's a moving charge, there will be a magnetic force acting on these electrons due to the magnetic field. We already know that the magnetic force is acting up on this electron as it is moving. So these electrons, as they move through this magnetic field, they will start to kind of curve upwards like this, okay? They will curve upwards like this. And depending on how fast they are moving, the curvature might be like this or this, however that's going to be. Essentially, after a bunch of electrons have collected at the top of this conductor, then what you're going to get is you're going to get a potential difference across the conductors because you have basically an charge imbalance on inside the conductor. Okay, so how many points is this one? It looks like 3, but so we kind of have to say 3 points here. This is what it could look like. So here's my first point. Now this is important, saying moving electrons, because if an electron is not moving, there's no way it will experience a magnetic force. So these guys will experience a magnetic force acting upwards. So that's the first step in thinking. Okay, so the next step here is that since you have these electrons all moving upwards, it means, or for you it would be this way, it means that you'll have a collection of these electrons at the top of the conductor versus the bottom, meaning you'll have some sort of charge imbalance. And then the last sentence, because of this charge imbalance, it will create electropotential difference between the top and bottom faces of the conductor. Okay. So hopefully that, so there we go. There were the 3 steps to break down our thinking. Okay, so now on to D. Woof, D and E. Wow, still a lot to go, guys. This is a lot of questions. So let's go. So D wants us to show, so let's read D first. The electric field between T and B is given by this one. So the top and bottom part of the conductor is the electric field is given by the potential difference over the distance of separation. We want to show that the voltage between the top and the bottom, which we call the Hall voltage, is given by V equals to V, small v, which is the drift velocity, times B, the magnetic field strength, and D, separation. So let's do this one here below. I'll use blue. Okay, oh, we need more space. Okay, so let's draw. Okay, I'm gonna use this space because it's getting pretty crowded up there. Okay, so let's say this is our conductor, and since the electrons will probably collect at the top, then we're going to have an electric field going down this way. Okay, so these are electric field lines. We know that the potential difference across these two is going to be equal to, based off the equation, the electric field times the distance of separation, which we know in the question. We know V, actually we don't know V, we're trying to solve for V, but it seems like we also need to know the electric field. Okay, so how do we find the electric field? Well, this kind of, now if you have no idea how to do this question, like you're looking at, well, how do I go from there to this, right? So you're thinking, well, somehow I need to show that this electric field is equivalent to VB. And how do I do that? So, like, for example, so for if you're seeing this question for the first time, that's going to be very hard. But what the first thing you might do, I know, remember when we talked about bumbling around a question? So the first thing you might think about is that, this kind of looks like, well, we know that for electric, we know this electron will experience a magnetic force upwards. And we know magnetic force is equivalent to QB times V. Q is the charge, V is the drift velocity in this scenario, B is the magnetic field. So this here, VB, kind of looks like VB here. So somehow this FM, this magnetic force, is involved. And somehow it has to do with electric field. So that's going to be your first hint. Okay, that's your first hint. And we know this electric field is used somewhere as well. So somehow there must be an equation that relates the magnetic field, the magnetic force acting on this electron, and the electric force acting on this electron. So you might think that, well, could they be the same? Meaning that this is going to be equal to E, and the electrostatic force, which we know is the charge times the electric field. You do notice the charges cancel out, and that E is equivalent to VB. But you can, when you are asked to explain this question, you have to think about why. Well, for me, I know where this is coming from, but for someone tackling this question for the first time, these might be the strategies you might have to take. So after doing this little bumbling around, you realize that the electrostatic force and the magnetic force are the same. So you're thinking, how in the world are they the same? If you this is where you kind of have to think about it a little bit more, and you just gotta have to pull your hair out in a way. But think about this, starting from the beginning of Hall effect. You have an electron. The minute you turn on the magnetic field, which is going out of the page in our case, so magnetic field gets turned on. Okay, magnetic field gets turned on. These don't exist yet. These electric field lines don't exist yet because no charges have accumulated. So as this electron moves through, and then bam, it lands on the top. Okay. It lands on the top. There's a collection of electric charges at the top, meaning that you're going to get the you're going to get electric field lines, a uniform electric field due to the collection of charge there. You're also going to get a magnetic field, or it was already there to start with. And notice the magnetic field is not going to change because it's just externally applied. But over time, as these electrons build a charge across the top, it will start to create as well an electric field. So there's our electric field, which is, I'll just write E there. Okay, so we have an electric field as well as a magnetic field. So if we put an electron here in the middle, we know it's going to experience a magnetic force, and it will always experience a magnetic force because the magnetic field is always there. But now there's an electric field, and we know that electrons move against the electric field. That's their natural tendency. Or in other words, this electron is not going to like the top of the conductor because there's so many electrons there, right? So there's also going to be an electrostatic force due to the field when there's enough electrons collected at the top, the next electron is going to experience the same force, the same magnetic force as well as the same electric force. So that's a certain sweet spot. A sweet spot is a threshold of which the maximum number of electrons can accumulate at the top, so that all the rest of the electrons that will come through will just move straight. Okay, will just move straight. And that's when you establish the Hall effect, this Hall voltage. So that's how you can show that the magnetic force is equal to the electrostatic force. Okay, so that's going to be, if I write this again, I don't know why this is there. This is going to be QVB equals to the Q times the electric field, in which the Q's cancel out, in which VB is equal to the electric field, so that we can substitute, we can then substitute VB in here, in which we're going to get the Hall effect potential difference equal to VB times D, and there you go. Okay, that's the question D. Okay, so in this question, you kind of just have to, if this is your first time seeing any sort of question, just work out where you have to go, where you start off with, and see if you can think about the steps in between. But never try to work backwards when you're showing your steps. Of course, when you're showing your steps, you always want to show steps moving forward. You can think backwards to help you along, but never work backwards. Never show your work going backwards. Like, I wouldn't go from V equals QBD and then show that VB is this and equals to that, and which then equals to V equals ED or something. So something to think about. Okay, so I bet this video is already super long, and if you're still with me, you're doing a fantastic job. So keep it up, okay? DI. All right, I think D-I is basically getting us to substitute things and just help us to make us calculate. But we're given the current in the conductor. The number of density of electrons. Okay, we get a bunch of numbers here. The cross-sectional area of the wire and the magnetic field. We want to calculate the Hall voltage. Okay, so we know that the Hall voltage is VBD. Okay, but we don't have the drift velocity. We'll have to find the drift velocity from the current. So we know that from this already. So I equals to Q NAV. Okay, so we probably have to solve for V to substitute in there. We can just do that quickly. We just divide both sides by QNA. That's okay, so I over QNA, and we'll have to substitute that in there, which we're going to get IBD on the top, and then QNA on the bottom. So I think we're provided with everything. We're provided with the current, the magnetic field, the charge, the charges are just electrons. So the density, the cross-sectional area, we're just not provided with D, okay? So if you're just absolutely stuck, and when I first saw this, I wish this question made a little bit clearer about the geometry of this conductor. So, I mean, the best that you can do at this point is you can't really assume a D value. The only way is to find a D value through some other part of this question, which they have not given to us. But the only way, potentially, is to assume that this cross-sectional area here is a square. If you assume that's a square, that's the only way you can get the D. Otherwise, this question didn't do a good job of explaining that. It also didn't do a good job of, well, I guess it could have just, if it wasn't a square, then it would have had to give you D. So that's the only thing you can work off of. So based off of that, if the cross-sectional area is a square, then to get the D, we just have to take the square root of the cross-sectional area to give us D, which is, what is it? 4.2 negative 6. Okay, 4.2 times 10 to the negative 6 meters, I believe. So, meters squared. So, taking the square root will take care of that. Okay, so putting that into our calculator, I get 2.049 times 10 to the power of negative 3 meters, okay? So I'm going to basically do the substitution. Let me just write everything down here. So here we have all of our numbers. The current, the magnetic field, the distance of separation, the charge of an electron, the number of electrons per unit volume, and this cross-sectional area. So let's just put all the numbers in. So I get 9.53 times 10 to the power of negative 9 volts. That is very tiny, and that's going to round to about 9.5. So 9.5 times 10 to the power negative 9 volts. Okay? Roughly that. Phew! D2, last one. Outline how the existence of the Hall voltage can be used to verify that the charge carriers in the conductor are negatively charged. So this one, you kind of have to use your right-hand rule a bit. So let's go here, down to the bottom. Okay, so on this diagram, I am showing you I have a proton here, and I have an electron. So we know that if we run a current, essentially, we know that the protons, the positive charge carriers, if the charge carriers were positive, they would flow in the opposite direction of the negative charge carriers, or if they're in relation to what a negative charge would do. Okay, so positive charge carriers would move towards, on your screen, it would move towards your left. If it's a negative charge carrier, it would move towards the right. Once a current of a specific direction is set, they will always move opposite to one another. So if the charge carriers were positive, using the right hand rule, and I just use my right hand, based off the so let's say these guys, let's say they move towards the left, okay? So using the right hand rule, I wish the magnetic field was going into the page. If you take a look at the positive charge carriers, they would get actually pushed upwards. So they would collect here at the top, making the top plate positive, okay? So that's the case there. If it's a negative charge, using the right hand rule but for the left hand, then these guys would actually move towards the other end. They would move they would move to the other side. So with the they will also get pulled up. Okay, so just like in the question, they will also get pulled up. So depending on the polarity of the charge, whichever charges are moving, you're either going to get a negative you're gonna get the top plate being negatively charged, or you're gonna get the top plate being positively charged. So when you measure the potential difference across the two here, it will be either the polarity would be exactly the opposite if the charge carriers were positive, and that has just to do with the nature of the current flow. If the current, depending on the current, whatever the current flow is, your positive charge carriers would move in one direction. If the charge carriers were negative, it will move in the opposite direction. Okay, so because of that, you're going to get so that helps you determine whether the charge carriers are negative, because the voltage established here would be it will basically create an electric field either going down, or it will, going up, my bad, or it will create an electric field going down. So then the polarity of your you're going to get the opposite pole for the opposite value for your potential difference across the plates if the charge carriers are positive. Okay, so that's essentially this question. All right, that's pretty long, but hopefully this but this question is very rigorous. I would say is one of the more rigorous questions, which will help you fully solidify your understanding of all the concepts in this unit. So I think if you can do this question, you're in pretty good shape. So there's some tricky ones in this process, but otherwise, whew, we made it! Congratulations for finishing this video and maybe this question. I thank you for watching and hopefully learned something useful in this video. Fat Mama Physics, signing out.